Purpose of this unit is to examine how our species uses energy and what effect this is having on our planet. We're looking at energy consumption through the lens of global climate change and global warming and the greenhouse effect and what that effect has on our planet. We have discussed all sorts of energy thus far. We've discussed potential energy, kinetic energy. We've touched on thermal energy, and all of these follow the law of conservation of energy that says energy cannot be created nor destroyed. Energy can only be changed or transferred. There's another name we can call that particular law now, and that's the first law of thermodynamics. Thermo means heat. Dynamics is the relationship between objects in terms of heat. So there are two ways to transfer energy between objects. There is the mechanical energy way number one, where the work done on an object increases the energy in that object or increases the kinetic energy in that object. I gave you the example of the guy pushing another guy in a cart because the guy in the green hat is doing work to the guy in the red hat. And so by the green hat guy doing work on the red hat guy, the cart and the gentleman in the red hat's kinetic energy is increasing. The other way is to transfer thermal energy from one object to another. And as we saw in the last unit, that is done because an object with a temperature of higher heat capacity can transfer energy to an object with a lower heat capacity or a lower internal energy. Heat transfers from high temperatures to low temperatures. So we as a society right now power most of what we need to power by using fuels. And the definition of a fuel is a substance that transfers thermal energy by changing its chemical composition. Fuels are not renewable, which tends to be a little bit of a problem. So I asked you to name some common fuels. I will give you one, gasoline. Think about why gasoline is a common fuel, and then think of a few others in your head quickly, and then move on to the next screen. What happens with fuels is that they undergo chemical changes. And when a fuel undergoes a chemical change, bonds in that fuel are broken and rearranged to make a new substance. And when these bonds are broken, energy is released. And when that energy is released, you end up transferring that energy to its particular surroundings. Those bonds will have a decrease in potential energy and an increase in kinetic energy because those bonds are not together anymore and the particles have more ways to move. The increase in kinetic energy has the ability to do work on another object. So in essence, this is kind of like the mechanical energy definition, but we look at the particles as opposed to the whole system. So here's an example. Burning coal, hot topic, current event item in the news now. So coal is carbon, oxygen, hydrogen. This is a typical structure of coal. And these all have particular components to them. If you look, some of these components are repetitive, but you will look and see that there's a lot of hydrogens, oxygens, and then wherever you see an intersection between two lines, those are all carbons. This is what we call a skeletal structure. And the purpose of me showing you this is to show you exactly how many atoms go into making coal. Now, imagine burning this coal. And when I burn this coal, all of these lines, which represent bonds, break. And when those bonds break, since there's so many of them, a considerable amount of thermal energy is released. However, not all of this thermal energy can be harnessed to do work. Here's a diagram of a coal-powered energy plant. I'm going to scroll down here, and what you're going to look at here is all of the different energy transfers that happen when we use coal as a fuel. So here's our coal here, goes from our conveyor belt into a massive furnace, and as the coal is burnt, you're transferring the coal's chemical potential energy to thermal energy. That thermal energy is transferring through the furnace, through the tube here, into the steam turbine. However, not all of that heat, not all of that thermal energy will make it from the furnace to the steam turbine. A lot of that thermal energy will leave the system and go out into the surroundings, in this case, the atmosphere. Also, you have the byproducts of burning coal, carbon dioxide, a greenhouse gas, and water, another greenhouse gas, even though not as predominant as carbon dioxide. And those substances also exit into the atmosphere or surroundings. However, the thermal energy makes its way into the steam turbine. The thermal energy heats the water. The water vaporizes. A phase change is occurring. So the water goes from being a liquid to being a gas. That gas has the ability to do work on the turbine. That steam actually turns that turbine in order to get it to rotate. And when you rotate a turbine such as this, you create an electrical field. And with that kinetic energy, you can transfer that to electrical energy that can then be transferred throughout the power lines and into the community. However, this is not a clean transfer. Not all of this energy is going to go directly from the turbine to the generator. You still will have a thermal energy that will leave the steam turbine into the ground. You will have unused electrical energy changing back to thermal energy, and that's why the casing around the generator gets warm. And this whole entire system, from start to finish, is only 30% efficient. That means you only get 30% of the energy you started with when you burn coal. So if you'd like to pause the video at this point and really analyze these energy transfers, you're going to be documenting and diagramming some of these for other types of power creating industries as well. So why does energy actually exit the system like it does? When we have an energy transfer, energy isn't a streamlined type of phenomenon. Energy wants to spread everywhere, and we call that an increase in entropy. I like to think about entropy as chaos. Entropy is the amount of disorder in the system. So let's say I decide to apply some energy to a pile of bricks that falls off a non-moving truck, and I want you to think about how those bricks will land on the ground. Are they going to stack themselves up in a nice, tight order just like this? Or when I throw those bricks off the truck, looks pretty chaotic? Well, law of nature says everything wants to tend to move to chaos, so when I throw those bricks off the back of the truck, I'll get a chaotic system. It's like when I transfer energy to any object, that energy will want to go everywhere. The entropy of the system will increase. And so that's why we can't have a clean energy transfers, because the energy doesn't go in the direction we just want. So, like I said, when the bricks were transferred from the truck to the ground, just like energy is transferred from one place to another, the bricks arrangements become more chaotic. Entropy of the bricks increased, just like the entropy of energy increases, and the energy will go everywhere, even the places we don't want it to go. This concept is called the degradation of energy, and it's defined as when energy is transferred from one form to another, some of the energy will have to be lost to the surroundings because the energy will go to the most entropic state possible. So here's me. Let's pretend this system is the coal furnace. This system is the turbine. I'm transferring energy from the furnace to the turbine, but there's a lot of energy lost to the surroundings. Here's a quick little review on the types of energy we're going to be talking about. So I've got thermal energy, which is heat, and heat energy is transferred between an object with a higher internal energy to an object with a lower internal energy. I've got electrical energy, things that light stuff up. I've got sound energy, which is what we can pick up with the eardrums we have in our ears. We have kinetic energy, the energy of movement. We have chemical potential energy. Chemical potential energy is stored in the bonds between atoms. Elastic potential energy, gravitational potential energy, based upon how high you are above a reference point. I've got electromagnetic energy. We can also call this radiant energy, and this also includes light. And those are the main types of energy we're going to be talking about in this unit in terms of energy transfer. Here's some examples of common energy transfers. A light bulb converts electrical energy to light and heat. Electric motor converts electrical energy to mechanical energy and heat. Battery. Notice what all of these have in common. All of these, you will have some of the energy lost to the surroundings in the form of heat. And that's crucial when we're talking about energy efficiency. So take a note on some of these because you're going to be doing a worksheet here in the next couple of days that's going to ask you to identify some of these energy transfers. In order to show how much energy is successfully transferred from system to system, and to show how much energy is degraded when making that transfer, we do something called creating a Sankey diagram. Named after Captain Matthew Sankey. He was a captain of a cruise ship that actually used that to show possible routes from one place to another in the ocean. But then you can use these Sankey diagrams in order to effectively map out energy transfers as well. So if you look down at the bottom here, Sankey diagram is basically one big arrow that gets smaller and smaller as you move through the energy transfer. So at the end of the arrow, you have 100% of all the energy. So back here, we'll call this 100% of all the energy that began in the system. Well, here I've got 9 units of energy that was wasted, and I'm looking at this in terms of the coal power plant. 9 units wasted in the furnace, so 9 units were degraded, leaving me with 91% of my energy left to transfer. Then, to transfer that heat to the cooling towers, 47% were lost. So then I can say 91 minus 47 is going to be 91 minus 47, if I can do the math in my head. 44% of the energy is left. Then I get down to here, where 3 units were wasted due to the friction in the turbine and the generator. Because the turbine and generator are not frictionless systems, I'm down to 41%. And this particular Sankey diagram is off by 1%, I believe, because if I take a look, this adds up to 41% at the very end instead of 40. And we did miss another step in between here where you ended up having the cooling station underneath the generator. So really a coal-powered plant is only about 30% effective and not 40%, even though we calculated about 41. Your task at this point is to go to Schoology, look at the Sankey diagram worksheet, and you're going to analyze different degradations of energy for different particular power generating facilities. You're going to practice drawing these. You can draw these in two different ways. You can do this electronically using Google Draw, or you can do these by hand in your notebook. You choose. Sometimes it's nice to draw them electronically because your lines are clean and nice. And we will check this off on Wednesday. Have a wonderful afternoon.